and welcome to all those who have joined us for today's MIT abstract featuring Martin Nisser. Today, Martin's going to talk to us about robots making robots and his research at MIT. I'm your host, Fatima Husain, and I'm a PhD student at MIT studying ancient Earth. Now, before we begin with Martin's talk, I'd like to cue you in to what an abstract actually is. So an abstract is simply a short summary of a greater work of research. And with this series, MIT Abstracts, we're bringing to you abstracts of research going on here every day on campus. For example, Martin's going to tell us all about his robotics research at MIT's Computer Science and Artificial Intelligence Laboratory. So without further ado, I'd like to give the stage to Martin. Martin has put on his camera. Welcome, Martin. Martin is our abstract expert for today. How are you, Martin?
Well, thank you. Thanks, Fatima. How are you?
I am doing all right. I am super excited for this talk. Again, I study earth science, so I want to know all about robots and the amazing work you do. So feel free to take it away.
Fantastic. Okay, so today I wanted to talk to you about building machines that make robots and how to make robots that make themselves. So if you've been following the news or movies lately, there's been a lot of discussions and some huge advancements in things like artificial intelligence and ways to make robots think smarter. But I think one of the key reasons we still don't see robots walking around our cities and helping us with our day-to-day tasks is because robots are still very expensive to make. So we're trying to think of different ways to build them in an automated way. So thinking about things like self-folding, self-assembly, or things like 3D printing, where ultimately we hope people like you will be able to design and print a robot from your homes with something like a 3D printer. And so the robots will just be able to fly or walk off the 3D printer themselves and start doing something helpful. But let me jump back for a quick second and just let me tell you about who I am and how I ended up here. So I think a lot of you are calling in from all around the world. So I grew up in a bunch of different places. My parents are from Sweden, but I grew up in Greece and the UAE. And as a kid, I always wanted to be an inventor. So I was interested in math and physics. And I really liked the idea of using math and physics to build something I could touch with my hands. And I think that naturally progressed into working with things like robots, which are kind of they're very physical things that we can see and we can touch. So ultimately, I ended up here at MIT in Boston, and today I'm a PhD student working on robotics and fabrication. And my name is Martin, in case I forgot to mention that. So maybe some of you are thinking, Martin, why do you think of these crazy, nutty ideas? And maybe why do people like you think of the same things? And I think the answer is a lot of us, watched a lot of probably too many sci-fi movies growing up. So to borrow something from a movie maybe you guys have seen, one thing is Big Hero 6. So in Big Hero 6, I think they translate this idea of self-assembly really well. So rather than building a robot that's really, really complex, that's all completely ready, they imagine robots as hundreds or thousands of mini robots that can assemble together to form the final shape. And once they're assembled, they can shapeshift from one shape into another in order to accomplish various tasks. If any of you watch some older things, there's also Star Trek. So in Star Trek, in some of the old versions, they have these machines called replicators, which are kind of like 3D printers, except you're able to print kind of anything you want. So whether it's a bunny or a glass or a finished robot or a machine. And so I think these ideas are really powerful of being able to kind of have robots that build themselves or being able to use a kind of 3D printer to build them for us. So I wanted to talk to you briefly today about 3 different ways of imagining how we might build things, robots or even general structures and devices in the future. So by 3D printing, self-folding, or self-assembly. So jumping into 3D printing first, there are kind of three kind of ingredients you need in order to 3D print a robot. So first, you need to be able to make the geometry. So you could either 3D print a robot from the ground up or use a laser to cut out geometry to make the final shape. You then need to be able to place or deposit circuit traces. So circuit traces are like conductive paths that you can use to provide electricity to all your different components. So in the case of a quad rotor, for example, the final ingredient you need is to be able to deposit these components, like four rotors and a central PCB, which is like the brain of a robot, and a battery, and to place those on your geometry such that they connect electrically via these circuit traces. And so here's a video of what this could look like. So in this one machine, we use a laser to cut out material in order to make the final shape of this quad rotor. Next, we use a kind of 3D printer to deposit or lay out these conductive circuit traces, which basically form these conductive paths between components so that they're connected to the battery. And finally, we use a part of this machine called a pick and place assembly to collect components like these rotors and the PCB and the battery and place them on the geometry that we already cut out. And then finally, we use a laser one more time to what's known as cure these conductive silver traces. And all that does is basically it heats it up so that it goes from not so conductive to very, very conductive. So it's much easier for a battery to pass electricity to them. And once that's done, we can just fire up the quad rotor and turn it on, and it can hopefully just fly itself directly off the platform. So another way we can think of making robots is by self-folding. So in this scenario, you can think of rather than making a robot in its final shape, you instead build it as a flat sheet of material, like you see on the left here. And by using these materials called shape memory polymers, we can actually program this flat sheet to self-fold into the target shape that we want. And so you see a progression of those images here. So this is what a video of that looks like. So by passing current through circuits on this robot, we can heat it up in such a way as to make it self-fold into a shape that we've pre-programmed it to fold into. And you see some of the smoke rising off the robots, which is just a result of them heating up so much. And then once they're self-folded, we can program them to walk or to a target location that we want it to go help out at, or program it to do some other kind of tasks that we think is helpful. We're not limited to like very simple shapes. We can even explore other shapes like here, self-folding kind of hexagon shape. But computer scientists working in a slightly different field have shown that you can actually self-fold things from a flat sheet to almost any arbitrary, any random final 3D shape. So there's theoretically, there's no limit to what shapes you can actually fold into. And then, so touching on this last idea, so self-assembly. So in that little clip from Big Hero 6, you saw this idea of what scientists call programmable matter, which is idea of taking a structure or a robot or like this chair and saying, rather than build the chair directly, we want to make hundreds of thousands of modules that can self-assemble and kind of assemble themselves into this target shape, in this case, a chair. And a different way of doing that is by imagining all these individual robots as cubes and having the cubes pivot with respect to each other around their edges in order to shapeshift from one shape to another. So this image on the right shows how this kind of mega cube in the top left could pivot itself in order to acquire the shape of this line that you see in the bottom right. And so one way we can kind of implement this idea physically is by building these cubes with a special kind of magnet embedded in each of their edges. We use these things called electromagnets, which are exactly like the permanent magnets you may be used to seeing, except we can actually change which way their magnetic fields are directed. And And by doing that, we can actually get two magnets to repel or attract each other at any time we want. So using this idea, we can create these cubes, and we can have them actually pivot with respect to each other by attracting each other to form a hinge, and then by repelling each other to kind of push or actuate this pivoting maneuver. And by combining all these things together, the idea is to use hundreds or thousands of these big cubes and have them shapeshift from one shape into another. So you might be asking, well, okay, you might be thinking I'm completely crazy by now. And so so what I've talked about today is kind of this this ultimate vision of how we can create robots and general hardware in the future. But there are some really interesting near-term applications as well. One of those is trying to build robots for space. So when you launch something to space, everything you want to put into orbit or to send to another planet has to be packaged into this narrow rocket fairing. So like the SpaceX rockets that you've maybe seen firing over the past couple of years. And these are only about 3 meters in diameter. So if you want to build something big, like a space station, the best way to do that is by making it in small pieces that can then be packaged into a rocket and then self-fold or self-assemble into a large structure once it's got to space. And here are some pictures of different pieces of work that people have been doing to do that. So people have been looking at trying to self-assemble space structures like the International Space Station in different ways, or by gradually making big solar panel arrays or big solar reflectors to try to beam energy from space to Earth. And I'm trying to accomplish that by sending up these structures in pieces and having them assemble once they're in space. And I don't have I'm not able today to share with you the experiment that, or some of the experiments I've been working on, but this video shows how we test some of these devices. So before we send them to space, we can get in what's called a parabolic, we do what's called a parabolic flight, which is a special kind of aircraft that goes up and down very quickly and puts you into free fall. So it kind of simulates microgravity, or what it would be like in space, for about 20 seconds at a time. So here you see me in the center and lots of people around me kind of floating around trying to do science while we're upside down and everyone's feet are flying into each other's heads. But I'm happy to talk more about that as well if you have any questions. But with that, yeah, I'm very happy. It was a pleasure being invited here today, and I'm happy to take any questions you might have. Thanks so much.
Thank you, Martin. That was super exciting. And I have 5 million questions I'd like to ask you, but I'm going to give the Nord Anglia students a chance to get their questions in first. So to start us off, Abhimanyu Singh is wondering, when will these Nord Anglia students be able to start making robots? What do you need to start making robots?
That's a great question. I think the easiest way to start is probably by getting your hands on this kind of a small circuit board, which is called, the one manufacturer is called an Arduino, and you can buy it for around $30 US. And using this Arduino, you can hook it up to a bunch of motors or batteries and that kind of thing, and build your own kind of little robots. But it's basically a brain which is very easy to program, and it lets you connect this brain to pieces of hardware like motors very easily. So I think that's a great place to start.
Okay, got it. I'm going to add that to my shopping list right now. Okay, so after I get an Arduino, what are some of the basic requirements of robots that I need to meet?
So in terms of kind of what you need to know, I think there are three main ingredients. So those three ingredients are kind of mechanical engineering, so how these pieces fit together and how to control your motors and make it move. The next is a little bit of electronics, so how to plug in your batteries and how to wire those batteries up to your motors and your brain and that kind of thing. And then the third component is computer science or programming. So writing a program that will tell your robot if it's like a car to drive forward, or turn left if it sees an obstacle, or turn right if it sees if it's about to crash into your dog or something like that.
Okay, got it. And we have a question from Giotsana, and she's wondering, how do you actually communicate with these robots in the moment, or after you've shot them out to space and they self-assemble? I mean, how do you tell them what to do?
Yeah, thanks, Giotsana. That's a great question. So generally speaking, you need to put a microcontroller, or like a brain, on each of the parts that you want to self-assemble. And then what people generally do is to transmit instructions from where you are using your computer over radio, or over Wi-Fi, or some other broadcasting system. And that will just wirelessly transmit the command that you send onto the brain of the robot, wherever it is. Then I'll have it execute that function.
Got it. Okay, so we need to install tiny brains so that we can communicate with robots. Got it. Okay. So Yashika is following up to this by asking, which robot is your favorite that you've built? Can you tell us about your favorite work? Maybe you can't mention the top secret work you're doing right now, but in the past, what's your favorite?
Hi, Ashika. Yeah, thanks for that question. I know they're like children. I don't have any favorites, but I think I really liked. Let's see. I think these cubes I showed you. I think I really like those because I think they just kind of move in a really cute way, and they yeah, I think it's very soothing watching a bunch of these cubes just on a table, just kind of pivoting back and forth, and making the shapes that we program it to make. So I think that's been a fun project to work on recently.
And when you're watching these cubes, get into their conformations, I mean, are you sitting at your desk in your office that you're in right now? I feel like I see some robotics parts behind you. Where is all this actually happening?
Yeah, this is happening actually right next door. We have so I sit in a lab in Boston here, and right next door to me, we have a little workshop where we have a lot of these robots and other hardware like 3D printers set up. Right now, I'm in just kind of a regular office that people like me do to just like write and talk to interesting people like you guys. So these are just a bunch of computers behind me, I think. Yeah.
It looks very much like my office in my lab, so I can relate to that quite greatly. But so that's super cool. So next door in MIT CSAIL, which is Computer Science and Artificial Intelligence Lab, you have your actual laboratory where you're seeing these things in action and building them. That's quite exciting. So Charvik is asking a very highly upvoted question. Charvik wants to know, why MIT for all this? Why did you come to MIT, Martin? I'm glad you're here, but tell me why.
Yeah, Charvik, that's a great question. Why MIT? So I think many reasons. I think so. I did my undergrad, my bachelor's, my kind of my first degree. I spent in Scotland, in Edinburgh, and it was kind of there where I was studying mechanical engineering, and I realized at the time that I wanted to do robotics, and particularly I wanted to build robots, and I was thinking about these different ways to try to make them by self-assembly and self-folding and that kind of thing. And just so happened that at MIT and in Boston in general, Harvard is just up the street. Actually, it's about a half-an-hour walk. And at Harvard and MIT, there were multiple professors who are working on exactly these ideas. And it's also, I mean, it's a great university. It's a great city to be in. If you look at Fatima's photo, she has some wonderful fall foliage and a great screenshot of MIT behind her. So it's just a beautiful place to be. So I think there are lots of intermatching reasons, but yeah, it's a great place to be.
I totally agree. So Martin, we have a lot of probably science fiction enthusiasts on the call. And, do these science fiction enthusiasts and students alike need to worry about robots taking over the world?
I hope not. I hope so. Yeah, there's a lot of There's a lot. I think I'm a little bit older than you, maybe. So maybe that's more your problem than mine. But I don't want to leave the answer there. So I think there's a lot of discussion in movies and the media um, that sound a little bit frightening. About robots and AI taking over. Um, I'm a little bit optimistic. I think we've seen some really rapid advances in the past few years, particularly since the advent of what's called machine learning, which is this way of robots rapidly being able to learn basic tasks, let's say. And I think when people get scared thinking about the future, I think they're basically looking at these past few years and seeing the advancements we've made and projecting that multiple years into the future, and thinking that things are going to keep building. The robots are going to get smarter at the same rate they've been getting smarter in the past few years. And but I think things will start slowing down, and the kind of techniques we've been developing over the past few years will ultimately not build what people are afraid they will build. So I think that's a long way of saying that I don't think we should be too worried, but I think we do have a responsibility to think about the possibility of things happening and trying to factor that into which problems we choose to work on, for sure.
Got it. Okay. Well, that makes me worry a little bit less right now, but you're right. We do have to think about these things very carefully as we proceed. And I wanted to follow up with a question from Aiden. So you were kind of talking about the rate of progress and how much advancement we made recently, and maybe that rate of advancement isn't going to be the same in the future. But Aiden's wondering, what are your thoughts on the use of quantum computing and quantum AI to build and make better robots? Do you believe that it'll be easier to program robots in the future?
That's a great question. I wouldn't. I'll try to tread carefully here because I don't know too much about quantum or quantum AI. But so I don't know whether I think quantum computing will certainly open up a whole host of new problems that we can solve, and that we can solve quickly, that we maybe were not able to solve previously. I don't know whether quantum computing itself will make it easier to program robots, but there are in parallel lots of people working on specifically how to make robots easier to program. Not just robots, so how to make programming languages in general much more easy to read and write. So one example of that could be if you've heard of the Scratch programming languages. They are basically ways of programming using building blocks that you can drag and drop onto a screen. And I'm not saying necessarily that that's the way we'll ultimately program, but it's these kind of ideas that people are playing around with to try to make things much easier to program. But I think you're asking exactly the right question.
That's great. So yeah, some of these students have heard of Scratch, and some of them do have coding experience as well with languages like Python, for example. Would that be useful going forward to learn how to program robots?
Yeah. Python's a great would be a great place to start. I think it's a very powerful language. It's just as powerful as all kind of the other main programming languages, but it's generally a little bit easier to get started for various reasons. But I use Python all the time, and I think if you're interested in doing things with robots or things for space, that would be a great language to learn, definitely.
That is really good to know because I'm learning Python right now. So can you tell us, Martin, when you're sending these robots into space, you mentioned an example of like perhaps assembling places like the space station, but can we send these self-assembling robots onto missions and have them, help us better explore our solar system?
Yeah, definitely. So I think there's so all the reasons I think we'd want to send these self-assembling satellites or structures into orbit around Earth. I think those same reasons translates perfectly to sending spacecraft out further into the solar system or beyond. So mainly the reasons why we want to self-assemble things is because it's just so hard to package a large thing into a small space, which is this, the rocket they have to launch in. And so if you want to send bigger things further away into the solar system, I think self-assembly would be a great way to accomplish that.
Got it. And one of our Nord Anglia students is wondering, when we are sending these self-assembling and easily packaged things up to space, are humans supposed to go with them to make sure everything goes all right?
Yeah, that's a great question. So I think in some cases, yes, and but ultimately the idea is to try to completely eliminate the need for human intervention. So it's really difficult to send astronauts into space because we want to keep them alive as long as possible. So if you don't have to worry about humans, then everything becomes much more simple. You don't have to send food up there. You don't have to send large quantities of water. You don't have to put air and breathable oxygen that's flammable up into your space station. So as soon as you eliminate the need to have humans assemble these things, the much easier and quicker we can do it. And a lot of the work being done today is exactly to try to accomplish that. So to try to have these systems that can completely control themselves to self-assemble correctly into their final shapes. Exactly.
Got it. And so, what happens if, some Nord Anglia students are wondering, what happens if something goes wrong with your robot or it starts to malfunction? How do you stop that? How do you control that?
Yeah, so that's a really interesting question because this is this is one of the main reasons we want to have these self-assembling systems. So if you imagine if I take my one robot, my Wally here, and something breaks in it, let's say it loses, its eyes, God forbid, then Wally can no longer see, and we have to send up an entire. If this Wally is in orbit around Earth, we have to design and build and launch a completely new Wally. But if you imagine Wally as an assembly of hundreds or thousands of little robots, like the cubes I showed you, or like in Big Hero 6, if you lose one of those little robots, or one of them breaks or malfunctions, you can just replace that single little robot with a new one. And so that's kind of one of the central ideas to this idea of what's known as programmable matter, or kind of swarm robots, is that if one part of your robot breaks, you can very easily replace it so that it can continue to function. But yeah, that's a great question.
And I think this, you mentioned like the idea of without these cubes and without this new technology that you're very hopeful about, we would have to send up like an entirely new Wally to space, for example. And that reminds me, some of these students at Nord Anglia are really interested in sustainability and trash and the idea of pollution. So we have a question from Sai Hassini, and she's wondering, can we use trash to make robots? Can we recycle robot parts?
Yes, Syed Hosseini, I think that's a really interesting idea. I think it's great that you're thinking about sustainability and that kind of thing. So I think there are a couple of answers to this, but the short answer is absolutely. So when we 3D, if you wanted to 3D print this kind of something in the shape of a Wally today, you would generally print it from plastic, from a single material from plastic. Then you've printed it, and then you have to trash it. You can try to recycle it, but the 3D printing materials for today are generally not very recyclable. So the chances are you wouldn't be able to do that. So one of the motivations for this self-assembly idea is that if you think of assembly as a kind of way of 3D printing things, you could assemble your modules, your robots, your cubes into your Wally shape. And then once you're done with your Wally shape, you can just program it to shapeshift itself into your new shape. And so it becomes you can imagine it as a kind of self-recyclable part. But if you're, there are other ways people have been thinking about using specifically trash for making things. So, people have, let me try to think of an example. So if you wanted to, going back to the 3D printing example, if you wanted to 3D print this poly, you'll see maybe that you have these wheels, which are, kind of detailed. You have this head, which is kind of detailed. You probably want to 3D print those. Then you have this big kind of cube looking thing, which maybe isn't that important to like the central task of this robot, which is to kind of walk and see. So what you could do is you could take like a box. Imagine this box was more cubey and less rectangular, and you put it in your 3D printer, and then you print the wheels and the head around the box. So you kind of, that way you don't waste your material on this big cubey structure. You only use your printing material to 3D print the kind of very detailed details like the wheels and the head, but use existing objects or trash to form the bigger parts of the robot. But that's a great question.
I think Iha's question really follows up nicely on this. So you mentioned some of the 3D printable materials that we use today are not really quite reusable or recyclable, and people are thinking about that. But how do you decide which materials you want to use for your robot in the first place? Like one student's asking, could you use glass in a robot? Do you need conductive wires? What do you need, and how do you decide?
Yeah, so I think there's I think it really depends on what you want your robot to do. So if you have a robot that you want to send to space, for example, space is really cold when you're not in sunlight, and really hot when you are in sunlight. So if you think of the International Space Station, this structure that's orbiting the Earth 15 times a day, the side of it that's facing the sun I think is upwards of something like 200 Celsius, which Fatima help me here, but I think it's like 400 Fahrenheit. And then the dark side, to the side that's not facing the sun, is about minus 270 Celsius, which is very cold. And so when you're dealing with those kinds of environments, you have to be very picky about what materials you use. But if you want to build if you yourself wanted to build like a toy, very important robot that could drive around your room, then I think you could use kind of any material. You could use plastics and tape and cardboard even. So like the robots the self-folding robots that I briefly showed, these were actually made of paper, because the task here was not to build a robot that could support really heavy weights or accomplish certain tasks. The goal was to show that we could program them to self-fold. And so we picked the materials that were easiest and cheapest to accomplish that goal. So yeah, it really depends what you wanted to do. But if you use glass, then make sure you don't cut yourself. Yes,
that's very good advice. Yeah, we will definitely be careful. And just for context, when you were mentioning those temperatures, for those of us who can't imagine how incredibly hot and how incredibly cold those temperature ranges can be, life can't survive at any of those temperatures that Martin mentioned. So if it's 200 degrees Celsius when you have sunlight, we don't have any life on Earth that we know can survive at that temperature. Similarly, we don't have any life on Earth that can survive at the extremely low temperature when the sun's not there. So that's just some context. I can't do some quick translation of temperatures right now, because I think of things in Celsius as well as a scientist. So that is quite good to know and to have that context. So Martin, we're wondering now, you showed us this really amazing video of you at the end of your talk, of you doing some top secret experiments. I can't ask you specifics about the experiments, but some North Anglia students and I are wondering, what did it feel like for you? What does it feel like to be in one of those planes and to feel weightlessness?
Yeah, it's certainly an interesting feeling. So it really feels like, you can imagine it really feels like falling for a long time. And I think it's if you've ever been, snorkeling or scuba diving or just, lying down in your bathtubs but not touching the walls. It's a little bit how it feels like. It's a strange feeling to not have your body in contact with anything. But there are some interesting things that happen when you're weightless for a longer time. So you get the same kind of weightlessness if you just jump and when you're in the air. And what we're essentially doing in this flight, or what astronauts are doing, are essentially jumping for a very, very long time. But when your body is in free fall for a long time, you get some interesting things like blood, for example, will rush up into your head because your body is adapted to pumping blood from your feet against gravity up into your head. And when gravity, quote unquote, doesn't exist anymore, your body's much more able to the way your body is pumping blood from your feet to your head is much more effective. So your head feels a bit funny, and if you look at astronauts or my face, you can see kind of your veins popping out a little bit. Maybe that's just my weird face, but to some other people, it's also kind of strange. You get a bit disoriented because there's a mechanism in your inner ear that kind of uses different cues like gravity and touch to tell you if you're upright or if you're lying down. And in 0G, that mechanism is kind of thrown off. So you feel a little bit disoriented. You don't really know if you're upwards or downwards. But it's certainly it's a great feeling though, despite all those things. And I would encourage you to try to explore that for yourself in the future.
And Martin, is it a once in a lifetime experience for you, or are you hoping to go back and do it again?
Yeah, I'm hoping to do it again. So I think so I will be doing it again in May of next year for a new experiment, and I might be going up later this year in December as well. So yeah, I think generally when you're trying to send things to space, you have to be really, really careful about testing it as much as you can here on Earth, because once you send it away, it's very hard to fix it. So we're trying to make this hardware as robust as we can before we send it.
Got it. I mean, for me, doing science and doing experiments at the lab bench is hard enough when I'm standing upright here on Earth on the ground. Can you tell us, how did you adapt to actually doing your experiments and not having the feelings you have here on the ground?
Yeah, sure. That was actually one of the hardest parts. Was trying to do science when you're upside down and when you get someone's feet in your face and you're trying to push them away. So that was certainly a hard lesson to learn. But you get the hang of it pretty quickly. Humans are really great at adapting to new circumstances. And so if you really need to pay attention on one of these flights, they have straps and handlebars where you can kind of hold yourself onto, so you can better concentrate on your experiment, which is what I try to do most of the time.
Got it. And now to preview this next question, I'm going to have to give a personal example just to give some context. So in my apartment building here in Cambridge, we have a robot that cleans our floors. It is named R2 Clean2. It's very cute. If I accidentally run into R2 Clean2 or push it out of the way, like it's in front of my door, R2 Clean2 will stop working and will crash, and someone will have to come and fix R2 Clean2 up. I mean, Nord Anglia students are asking, when and how can we get robots to respond to their environments and interactions from humans? How do we teach them to adapt in the moment? Is that something we have to hard program for the beginning, or is this a functionality that we can gain with time as we make progress?
Yeah, that's a great question. It's kind of one of the it's really like the central question to robotics today. So people all around the world in all your countries are working on exactly this problem. I think the problem really is that it's very difficult to program in the kind of rules that we take for granted as humans. So we as humans, when we look around the world, you know, if you were looking at in this room, for example, and you look around, you know, the things that are around me, you can tell that there are computers there. You know that a computer has hard edges. You know, you can tell by looking at it roughly how much it weighs. You know that if I jump up, the next thing that's going to happen to me is that I'm going to fall down. So you have a concept of gravity. You know that if I move further away, then I'm going to get smaller in your field of view. And so there's lots of these kind of simple ideas, I'd say, that are very difficult to program into a robot, because it has to know about a lot of objects. It has to know about gravity. It has to know about what sharp means. It has to know that if I pick up a piece of glass, I shouldn't squeeze too tight. Or like an egg, I really shouldn't squeeze too tight either. But if I pick up my phone, I can hold it, you know, strongly to make sure that it doesn't fall and break. So I guess I'm just trying to give some examples that yeah, it's a really challenging problem to try to get robots to respond adaptively to their environments, because it's very hard to teach them exactly what the environment is. So I hope that makes sense, but otherwise it's a great question to ask someone smarter than me.
No, I think what you're saying makes sense. And if I understand correctly, I mean, would it be fair to say that we have to ingrain and teach robots this concept of this intuition, or this intuitive physics that you and I take for granted and that we learn as children? I mean,
exactly. Yeah. So that's you know, if you've heard of this concept known as machine learning, that's really the way it's been applied to much of robotics today. So rather than teach a robot to program it, you know, with literal lines of code that there is gravity and this is how gravity acts, and if something's sharp, then it's going to break me. If I'm dropped, I'm also going to be broken and angry. Rather than kind of programming in all these rules, we can just let the robot free to walk around the earth and bump into things, or have an AI system watch footage of you know, cars going down the highway and turning at certain points to, you know, stay on the road. And just by feeding them lots and lots of this data, so by having them walk around the world or watch footage of the world, they will actually just learn these rules. So they will learn that if someone jumps up, the next thing that's going to happen is that they're definitely going to fall down again. But then the question is the more advanced question that people are now trying to figure out is, have they really learned those rules, or have they learned something similar? But that's yeah, that's a huge question. But you're asking the right things, so it's a great question.
Awesome. And now, Martin, I think you have inspired a lot of future engineers and roboticists today. Let's say they're thinking, you know, I want to be just like Martin. I want to do the cool work he's doing, or I want to build R2 Clean 2. You know, what advice would you give them going forward as they proceed in their educations?
Yeah. So I think the thing I would really just say is, you know, try to do activities or take subjects and engage in things that are, you know, meaningful and interesting and fun to you. So, you know, don't necessarily do just the things that you think are the right things to do to make you successful. Like, do the things that you really find that you're really passionate about. Because I think if you choose things that you're passionate about, you'll work really hard at them, and if you work really hard at them, you'll ultimately become successful and really great at them. I think, just to give an example, so I did mechanical engineering in my undergrad, and I never knew, I had an interest in space, but I never really knew what I'd be doing years later. But in my first year of university, I took a couple of options to do as like extracurriculars or like optional courses, and I chose astronomy and cosmology just because I was kind of interested in it. And then I didn't think about space for multiple years. But 5-10 years later, I was able to kind of use those skills and translate that into something that I work on today. So I would just say, do what you think is interesting.
Got it. I think that's really solid advice. So unfortunately, though, Nord Anglia students have asked us hundreds of questions today, and I told you, Martin, I have 5 million more to ask you at another time. I'm unfortunately going to have to start our conclusion and share with you all our next talk. So next time for MIT Abstracts, we're going to talk about something quite different from what Martin discussed with us today. Instead of robots, we're going to talk about biology and what happens when our food makes us sick. How do microbes do that to us? What's that like? And how do we study that? So Yami is going to give us that talk next time, so be sure to join us. But I wanted to say, if you liked aspects of Martin's talk today that you need to replay and you need to write down, like, I need to buy an Arduino chip, or I need to think about these materials, you can rewatch Martin's talk. We'll post the recording within a week or so on Global Campus, as well as YouTube. And the same will go for Yami's future talk. So if you can't make it and join us next month, we'll post that too. And even better, if you're new to MIT Abstracts and you want to see past talks on a different style of robots, for example, or climate change, or synthetic biology, you can go back to our recorded abstracts and watch the older videos of those MIT experts and their talks. So I'm really excited for you to join us however you can. And now I just want to quickly thank the MIT Nord Anglia Education Collaboration for making this series possible. We wouldn't be able to do it without you. We wouldn't be able to bring such cool speakers like Martin to students around the world without your support. And lastly, I'd like to thank Martin. Thank you so much for your time and for sharing your expertise with us. This was super, super cool.
Thanks so much for having me. Yeah, it's a pleasure to talk to everyone today.
Excellent. Well, I'm going to let you all go off and enjoy the rest of your days. Thank you again for joining us, and goodbye, Martin.
All right, goodbye, everyone. Have a good day.
Goodbye. You too. Bye.